Recently in this course, we learned that stable atmospheric conditions can lead to a buildup of air pollutants. Thunderstorms, on the other hand, form when the atmosphere is unstable. We now are going to look at this topic with a little more detail. Meteorologists look for situations that might make the atmosphere unstable because this could warn of severe weather. We start with relative use to understand conceptual tests that can be performed to determine whether the atmosphere is stable or unstable. You simply take some air and isolate in the air parcel, this kind of an invisible balloon. At this point, the air inside the parcel is exactly the same as the air outside, same temperature, density, and pressure. We assume that once the air is sealed in this parcel, it cannot mix or exchange heat with the surrounding air. Next, imagine lifting this air. The air parcel will expand and the air in the parcel will cool somewhat. After being lifted, the air inside the parcel may have a different temperature than surrounding air outside the parcel. This is because the inside of the parcel is insulated from the surrounding air. In some ways, this is like getting inside an automobile and drive up to the top of the mountain. You might have the heater or maybe the air conditioner running the car. In either event, once you arrive at the mountain summit, the air inside the car would probably have a different temperature than the air outside. Once we have lifted the air, we let go the parcel and watch to see what happens next. If the air comes back to where it started, the atmosphere is called stable. If the air continues to rise, the atmosphere is unstable. In the figure above, the air in the parcel has ended up colder and denser than surrounding air. In this case, the parcel would sink back to the ground. Now the lifted air parcel has found itself warmer and less dense than surrounding air, like a hot balloon. Think about it. It will continue to float upward on its own. That indicates an unstable situation. We need a little more information to be able to perform the test described above. First, we need to know how quickly a rising parcel of air would cool. Unsaturated air, so where the relative humidity is less than 100%, always cools at a rate of 10 degrees Celsius per kilometer. This is known as the dry adiabatic lapse rate. The term lapse rate just means rate of decrease of increasing altitude. Adiabatic means that heat is not being exchanged between the air inside and outside the parcel. Saturated air cools a little more slowly. We use an average rate of 6 degrees Celsius per kilometer, the moist or wet adiabatic lapse rate. As saturated air rises, expands, and cools, condensation releases latent heat inside the parcel. Remember the concept of latent heat, or exchanging phases from gas to liquid? The latent heat energy offsets and reduces the cooling due to expansion. There isn't enough latent heat energy to cause the rise parcel to warm. We also need to know the temperature of the atmosphere at the different altitudes above the ground. The atmosphere can do just about anything. So the middle figure shows temperature decreasing at the rate of 8 degrees Celsius per kilometer, the environmental lapse rate. The left and right example shows the air cooling more slowly and more rapidly, 1-to-1 with increasing altitude. Usually, atmospheric temperature does not decrease at a uniform rate as I showed above. A more realistic example is as shown below. Plot of temperature versus altitude is called a sounding. We now have all the tools we need. In this first example, we assume the environmental lapse rate is 4 degrees Celsius per kilometer. This is shown in the left column of figures in the figure above. The next two columns show the temperatures inside the rising parcels of unsaturated green and saturated orange air. They cool at 10 degrees Celsius per kilometer and 6 degrees Celsius per kilometer. Let's see if you change the environmental lapse rate right now to 11 degrees Celsius per kilometer. in this new example. Now, because the atmosphere is cooling so quickly with the increased altitude, lifted parcels of both unsaturated and saturated air end up warmer and less dense than the surrounding air. When released, this parcel will continue to rise on their own. The temperature is absolutely unstable in this case. The third case will pick an intermediate value, 80 degrees Celsius, let's say, per kilometer, for the environmental lapse rate. The atmosphere is conditionally unstable. A rising parcel of unsaturated air ends up cooler and denser than the surroundings. A parcel of saturated air, which cools at a slower rate, ends up warmer than the air around it. The condition for instability is that the air must be saturated. We'll leave the environmental lapse rate the same for the last and most instructive example. In this case, the parcel of air starts out unsaturated. It becomes saturated when lifted to 1.5 kilometers altitude, once it has cooled to the temperature of 0 degrees Celsius. This is called the lift condensation level, LCL, as you should see cloud begin to form at this point. If you look outside, maybe some cloudy day, you might notice several clouds called cumulus clouds. They have this flat base, so that is the lift condensation level. From the point of upward, the rising parcel will cool at the most moist adiabatic rate. Initially, the rising parcel is colder and denser than the surrounding air. If you lift above 3 kilometers, the parcel air finds itself warmer and less than the air outside. If lifted just a little bit beyond the 3 kilometer altitude, the parcel will be able to continue the rise on its own. 3 kilometers in this case is the level of free convection, or LFC. The atmosphere is conditionally unstable in this case. A rising parcel must first of all become saturated, then must be lifted to and just above the level of free convection. The value of the environmental lapse rate is one of the main factors that determines whether the atmosphere will be stable or unstable.